Hi, I'm Valiant Cheng. If you often come across terms related to sockets in your work or studies but have never delved into their essence, I believe this video can help you. Routing is an unavoidable part of computer systems, and sockets, as a crucial component of computer networking, hold significant importance. However, even though we may have learned about basic networking concepts like TCP and IP in books or classrooms, our understanding of sockets is often lacking. You've probably encountered many socket-related errors, logs, or mentions in technical articles, and perhaps you formed a vague impression of them. But when it comes to what they actually are or how to grasp and understand them, things might still be unclear. I once had the same doubts, so I tried to find answers to these questions. That's when I came across the book Unix Network Programming, Volume 1, The Sockets Networking API, which ultimately helped me resolve my confusion. However, although this book is a classic that has stood the test of time, while reading it, I noticed some content that deviates from the current era's context, which may not align well with the needs of most audience today. Therefore, I hope to distill the essence of this book and combine it with my own knowledge, experience, and background to help people with similar needs resolve their doubts more efficiently and understand sockets better. Of course, a deeper understanding and mastery would require more extensive coverage, but this video will prioritize the most common and frequently used topics. If you need more detailed explanations on specific subjects, you can give me feedback on those topics. Also, please note that my personal experience may have considerable limitations. Feel free to watch selectively and consider critically. If you spot any mistakes or omissions, you can point them out for correction. First, we must clarify what a socket is. I believe viewers with some basic networking knowledge are aware that computer networks have a very clear layered structure. From the lowest physical layer and data link layer to the upper transport layers like TCP and the application layer, each layer has its own responsibilities and corresponding functions. While this layered model of networking is very helpful for understanding the hierarchy, structure, and data flow patterns of networks, it also introduces significant complexity and overhead when we actually want to use it. Imagine if, to send a single data packet, you had to construct everything from the HTTP layer all the way down to the data link layer. The implementation cost would be incredibly high. In this context, the creators of operating systems provided strong support by shielding the underlying complexities and abstracting a unified interface for network operations, making it easier for higher-level users to utilize networks. This unified network operation interface is the socket system. The word socket means an electrical outlet. When using electrical appliances, people don't. You need to understand how electricity is generated or transmitted. Instead, they simply and uniformly plug the appliance into the socket to utilize the complex power system. This is a great analogy for how we use sockets in network operations. So, how do we use sockets? A socket is an abstract interface system, which you can think of as a set of usage protocols or an API. Since it's a mechanism provided and encapsulated at the operating system level, its specific usage requires system calls. Common socket-related system calls include socket. Creates a socket equivalent to finding an outlet. This is the first step in all socket operations. The socket interface system offers many types of sockets, each with its own use cases, which will be explained in detail later. Get socket, sat socket. Retrieves and sent socket options, similar to checking whether an outlet is two-pronged or three-pronged, or what its voltage is. These are very important operations, as many interaction details with the socket are controlled through these methods. They have different applications in various scenarios, which will be explained in detail later. Binding operation, equivalent to plugging an appliance into the outlet. This means binding a specific IP address and port combination on the machine as an exclusive resource, preventing others from using this combination. It's a way to declare ownership of network resources. Listen. Transport layer semantic listening operation. Passively waiting for another network entity to initiate communication, usually a connect operation, with itself. That is the bound IP and port combination. Accepts. Transport semantic connection confirmation operation. Acknowledging the relationship between a network entity attempting to establish a connection and itself. Once accept is called a formal transport layer connection is established and subsequent data exchange can begin. Connect. Transport layer semantic connection operation. Connect into a transport layer network entity. That is protocol plus IP plus port number. where the protocol could be TCP, UDP, or another layer 4 protocol. For TCP, this is the classic three-way handshake process. Shutdown, close. Transport layer semantic closing operations, terminating an established connection. Send to. Transport layer semantic sending operations. After a connection is established, if one end wants to send data, it can use these operations to transmit the data to the other end. The encapsulation of data packets at each layer is hidden beneath these operations. Receive. Receive from. Transport layer semantic receiving operations, the counterparts to the previous group of calls used to receive data from the other end. We can see that many of the above system calls are related to transport layer semantics, which indicates that a large part of socket functionality provides interfaces above the fourth layer, the transport layer, of the network. However, not all operations are based on the fourth layer. Later, we will learn about sockets based on other layers as well. Alright, now let's answer our earlier question. What types of sockets are there and what are their purposes? Common socket types include TCP, sock stream. This is the most commonly used type, providing network operations at the TCP level. UDP, sock datagram, another widely used type, offering network operations at the UDP level. Unix, AF Unix, also very common, often used for direct communication between processes on the same machine. It relies minimally on the network protocol stack, making it faster and more reliable compared to regular local network socket communication. RAW, SOC RAW, used for direct access and manipulation of lower layer packets such as IP or ICMP. This is employed in scenarios like sassing and processing IP layer packets, such as in programs like Ping, TracerO, or even implementing transport layer protocols other than TCP or UDP. Netlink, used for communication between user space and kernel space, such as retrieving routing information, network configurations, or other data stored in the kernel. Packet PF packet, used for direct access and manipulation of data link layer packets, notably. Common packet capture tools like TCP dump do not use this socket type for their work. Instead, they rely on the BPF interface, which is a separate method for accessing and handling data link layer packets independent of packet sockets. There are several other socket types, but they are used less frequently compared to the ones mentioned above, so we'll omit them here. As we can see, there are many types of sockets, far beyond just the fourth transport layer. Through different socket types we can perform many other operations, even outside the scope of networking. Over time, sockets have evolved from a network communication tool into a standard interface system for data communication operations. Earlier, we mentioned that sockets have many cockrobotics options, so what are the most commonly used ones? For most developers, the most important socket options are those related to TCP and UDP. The main ones include Socket Keep Alive, enables TCP's Keep Alive mechanism, periodically checking whether the connection is still active to prevent zombie connections caused by abnormal client disconnections. TCP No Delay, disables or enables the Nagel algorithm, an algorithm that aims to send data packets as quickly as possible. For applications requiring low latency, disabling the Nagel algorithm can prevent delayed packet transmission, though it may increase network traffic. Socket Receive Buff Socket Send Buff. These set the size of the socket's receive and send buffers. Adjusting the buffer size can optimize socket throughput performance, which essentially increases data transfer speed. Socket Linger controls whether the socket immediately sends unsent data packets when closing or waits for a certain period. Adjusting this option can reduce the number of sockets in the time-wait state. Socket Receive Timeout, Socket Send Timeout. These set the timeout for receive and send operations. If you don't want to be blocked indefinitely during network I/O operations, you should configure these parameters. TCP Cork. When enabled, TCP data won't be sent immediately until the buffer is full or the send function is explicitly called. This optimizes TCP data transmission by avoiding small packets, improving network utilization. It works in contrast to the No Delay option. Socket Reuse Port allows multiple processes or threads to bind to the same port, enabling kernel-level load balancing. As we can see, many of these socket options are closely related to the details of send and receive behaviors. These details can sometimes have subtle effects when we use them in practice. In daily usage, many underlying frameworks and third-party libraries handle these configurations for us. However, when our actual intent conflicts with the default settings, we need to make targeted adjustments. At that point, understanding these options and their tuning effects becomes crucial. Beyond these, other types of sockets, like broadcast and multicast, also have many specific Coxburdle options. These can be explored in specific scenarios, so we won't list them in detail here. Alright, in this video, we've covered some of the most fundamental theoretical knowledge about sockets. These concepts form the basis for understanding all socket-related applications and issues. Some topics in the video may not have been explained in extreme detail because I wanted beginners to grasp the essentials systematically, without getting overwhelmed by overly complex details right from the start. Once we have a structured understanding of the core concepts, we can then explore more complex details rather than trying to learn everything exhaustively from the outset, which isn't very realistic. Progress in knowledge and understanding often follows a spiral ascent, not a single leap to mastery. Additionally, I recommend that after watching the video, you review the text version to consolidate your understanding and explore points of interest further. This will help deepen your comprehension. You can find the link to the text version in the video description. If you're particularly interested in any of these details, feel free to mention them in the comments section. I'll consider going deeper into the topics based on your feedback. In the next video, I will introduce some very common real-world scenarios where we interact with sockets. These are situations you'll likely encounter. Through analyzing these practical examples, I hope to help you gain a better understanding of sockets and related knowledge. Thanks for watching.